Hi everyone and welcome to this video. In the previous video we had talked about the fundamentals of machine learning, and I hope that you got better intuition about the fundamentals of machine learning, which includes some of the overfitting, underfitting, cross-validation test, set, training set, and what is machine learning, what are the types of machine learning, supervised learning, unsupervised learning, and reinforcement learning. Okay, so when I hope that you got familiar with that, and if not, be sure to comment in below. I'll be happy to assist you, but please be sure to comment in below on the video that you have problem. Okay, and in general you can comment in any video, or if you want assistance you can simply message me on LinkedIn or Instagram. The link will in the description down box below. Okay, so in this video what I planned is I had prepared a notebook, a very good notebook, full equation notebooks like for you, and what I'm going to do is I'm going to make you familiar with linear regression, everything you need to know about. Okay, so you'll be mastering linear regression in only one video, and this will be a long video, so please be sure to sit anywhere and pull out this PDF. The link in the description down box below. I'll be given a PDF and then download from there. And after that, what you have to do, you have to come on there and then start along with me and open your Jupyter notebook or a Colab or Watson Studio, or if you're in Azure Machine Learning Studio, whatever you are on. Okay, so open that and just code along me when I was coding. Okay, so let's start talk about what we are going to study. First of all, let's study what is linear regression, and then we'll talk about hypothesis function, then we'll talk about cost function, then we'll talk about how actually cost function works, and this is for multivariate linear regression. We'll talk about just in a second what is that. Okay, and then we'll talk about a normal equation, and then batch gradient descent, and then we'll talk about implementation of that batch gradient descent, and then talk about some of the code and like equations, and then we'll talk about the learning rate alpha, and then we'll go on to the how to choose the learning rates. It is a hyperparameter we'll talk about more about later on, and then we'll implement linear regression from very scratch without any help of libraries. And okay, so after we develop the linear regression from very scratch, and then we will develop the linear regression with scikit-learn. Okay, so in scratch you will have intuitive understanding of how actually we can make the linear regression, and then we can implement, and then we will also do with scikit-learn. Okay, so this was the overview of what we are going to study. So let's start talking about what is a linear regression. So linear regression is a supervised learning algorithm, and this is for specifically for regression task. Means if you want to predict the stock prices, or you want to predict the house prices, or anything you want to who has a continuous data and is supervised learning. Okay, so you can use regression over there. Okay, so it is one of the powerful and most used algorithm that you will ever see. Linear regression mostly divided into linear regression with univariate and a linear regression with multivariate. Okay, so let's talk about what is that univariate and multivariate linear regression. Okay, so what I'm talking about first is divided into univariate, or we can say one variable, and another is divided, and one more of this is a multivariate, which is multiple variables. Okay, just don't focus on here. I will talk about just a second what is that. So we classify linear regression under two variables, into two types. Univariate linear regression and multivariate linear regression. Univariate linear regression usually for the teaching purposes people make use of, but I think that we should start with directly multivariate, because univariate, what does it mean? It simply means that you have one feature, let's say the size, and you have to predict the price, and you will be most rarely see these kind of problem statement that you have to predict the price of the house based on the size of the house. But this will generally you will not see in machine learning or data science journey in a real world, because I want you to be familiar with the real world. So that's why I'm not going to push out to you and go with univariate. We'll directly jump into the advanced concept, okay? But we'll start from very basics with understanding of univariate also. So what does it univariate means? It simply means you'll be given only one feature, and the basis of only one feature X, you have to predict the price of the house. But in case of multivariate linear regression, what you have, you are given the size of the house as well as the price of the not the price of the house, we have to predict that, a number of bedrooms of the house, then number of floors, and then number of fans, and there are a lot more, even 1,000 columns or features. So we usually denote x1, x2, x subscript 3, x subscript 4, x subscript 5, and all the way down to whatever the number of a column is. So let's represent J. Okay, so it is used because in univariate you are only denoting with x, but in multivariate you have to for different features like x1, x2, x3, x4, x5, all the way down to the x. Okay, so this was multivariate and univariate linear regression, but general you will see this a lot, means the multivariate linear regression. Okay, so what does linear regression looks like? So let's take an example. So see here that we have a scattered data. So we have a scattered data. And what you have to do, you have to make predictions onto this data by giving to the linear regression. So you can see here, this is a very scattered data, and what you have to do, you have to make a straight line for making the predictions. And you might be thinking, hey Ayush, what is this? You were a little bit confused. So let's understand it a little bit more intuitive way. Okay, so let's take an example that this is for 0.50. You will take here, and this is the data point, and this is the answer. So this is the y-axis, this is the x-axis. So by checking this one, you can see here, and here you can find the answer. So here the answer is 5. Okay, so 0.50, we give the input as a 0.50x, and we get the output 5. Because of this line, we are able to find this 5. Okay, let's take one more example that you want to predict for this data point. Okay, so you will go from here and on the y-axis, and it will generate so slightly more 6.65. Okay, so if you provide 0.85, you will get 6.65. Okay, so this is x-axis, this is y. Okay, so you provide input and you're going to get output because of this straight line, or we can say the hypothesis. Okay, so this is usually called the hypothesis. Okay, so you might be thinking, hey Ayush, how I make this a straight line, or how I make this hypothesis? So for making this straight line, making this a straight line, we have a function h of x. We have a function known as h of x, denoted as a theta 0 times the x0 plus theta 1 times the x1, all around to theta n times the xn. And I know that you are very confused just now. So just hold on, I will make you understand. Okay, so what is y hat? Y hat means your prediction, because by using this straight line, we can remove this. No need, we can remove this. But this equation forms a straight line. This equation forms the straight line, and from this we are getting the output. So we usually denote output as a y hat when we have a multiple output. Okay, not a y hat, I can say y, which is our output, and we give hat because we have a multiple features here. Okay, so we usually denote a y hat here. Okay, so let's understand what is this h of x. Don't focus if you're uncomfortable with y hat. It is just you are getting output. You're getting output which is stored here. Okay, so what is h of x? H of x is a function that makes us a straight line. So what is this theta? Well, theta 0 times x0, theta 1 times x1, all the way down to theta n times the xn. So what is that? In the above equation, you can see theta 0 times x0 is the bias term, also called the intercept. What does that mean? Again, the same thing happen, that we usually denote x0 equals to 1. X subscript 0 equals to 1. And if I multiply theta 0 times the 1, you will generally get theta 0. It's obvious. So we usually don't write x0, but for understanding, I have written x0 there. And then we are adding theta 1 times the x1. So let's understand more intuitive way. So here theta 0 is the bias term, also called the intercept. And if you don't know about intercept, be sure to search online and then you will know that. But bias term means from where you're going to start this straight line. So let's say you want to start with here, and whether you want to start. So if your theta 0 equals to 0, then it will start from origin. If your theta 0 equals to 1, your line will start from here. If your theta 0 equals to 2, your line will start from, let's say, 1, 2 is here. And if it is theta 0 equals to 0, it will start from here. So it's understanding your intercept. Okay? And these theta 1, theta 2, theta 3, all the way down theta n are the feature weights. And you might be thinking, hey Yush, what is that? Theta 1 is the coefficient of x1. Theta 2 is the coefficient of x2. And again, x1, let's take an example, x1, x2, x3, all the way down to xn is the features or input values. So let's assume that x1 is equal to the number of bedrooms, number of floors. So we have to give this as a x1 as the input, and with this theta 1, theta 2, theta 3, theta 4, we are going to get the output. So what we have to do, we have to learn these parameters. Theta 1, theta 2, theta 3, all the way down to theta n. So we have to learn this parameter. So we have to choose the perfect theta parameter that will give us the y hat. And this equation makes a straight line. And just what we have to do, we have to find out what is the bias term and all the feature weights. We usually know the coefficients of the dat. Okay? So let's assume that is the let's assume that here what we are going to do, what we will do, we will put theta 0, theta 1, theta 2, all the way down to theta n in a joint vector theta. Okay, so I hope that you understand what is theta 0, theta 1, theta 2, theta 3, all the way down to theta n. These are the feature rates, and we have to find the perfect theta. This is called the parameter, and we have to find this perfect theta parameter. Okay, so if you find the perfect theta parameter, and then you are good to go. Okay, so we'll talk about how to find the best theta parameter. So that's why we are learning our cost function, gradient and all the stuffs for this theta. Okay, so we have to learn this parameter, and we will do some kind of vectorization, because this will take a lot more time, and we want a vectorized, because you usually see that in we want a vectorized form of anything. We want a good thing which is vectorized. So what we will do, we will take out all this theta. Means, let's say we have taken out theta 0, theta 1, theta 2, all the way down theta n, and we'll put this into a vector of n-dimensional, and then into a giant vector theta. Okay, so in only one theta we will put this vector. Okay, all thing here, and we usually denote this as a parameter vector, parameter vector. And why it is called parameter vector? Because you can see these are the parameters, and sorry, not x2, these are the parameters that we have to learn, and that model has to learn. and then using this equation we can simplify the predict. Okay, so what we'll do, we will put this theta into the parameter vector and all this kind of feature weights in the giant vector theta, and then we will put x1 x0 is eventually equals to 1, so we don't focus onto that. So x1 x2 all the way down to the xn, we will put this n-dimensional vector or feature vector. It is called a feature vector. The reason why, because we are giving input to them, so it is called the feature vector into a giant vector s x. And then what we will do, we will do the dot product of theta and x. We'll do the dot product of theta and x. So if we do the dot product, x1 theta 1 x2 theta 2 x all the way xn, so it will cause a broadcasting. So you can write x0 also, so it will be x0 times the theta 0, x1 times the theta 1, x2 times the theta 2. So it is called the broadcasting Python. Broadcasting means with the dot product it will product all the dot over, or we can say the x1 times it will form this equation after this, because this is the vectorized form. So if you will multiply two vectors, it will multiply element wise. Okay, and I hope that you got better intuition what I'm trying to say here. It's already 16 minutes we have spent upon this. Now we have done a lot. Now this is the vectorized form of the equation. We'll make use this only. Okay, again you can read it here what I've written here, and you can the notes will, all the Jupyter note will be given to you, and it takes a lot of time to let me show you how this equation makes. I had never used my pencil for writing this, so you can try out different equations upon that. Okay, so let's take one example, and be sure to subscribe this YouTube channel. Okay, so here let's for a second example, let's say we have a univariate linear regression. So on the basis of the size of the house, we have to predict the price of the house. So here h of x, so if you have two features, first is the theta 0, which is a bias term, times the x0, which is always equals to 1, plus one feature, we have a size theta 1 times the x1. If it is bed number of bedrooms, we'll write another. So we have only two features, so we'll write that. And then let's take an example. We have taken theta 0 equals to 2.5 and theta 1 equals to 3.6. Okay, so if you have taken theta 0 equals to 2.5 and theta 1 equals to 3.6, so we can write this equation as y hat equals to h of x, and then you can put the size of the house, and then you will get the price of the house, which is the y hat, which will be stored in the y hat. Okay, so let's put 2000 the square feet. It is just a crappy thing, a dummy thing, so don't focus on that what I'm trying to say here. But for the sake of example, let's change this as. Okay, so you can put 2000 and you're going to get this. Okay, now take a break and then come back. Okay, so I hope that you have taken a break and then came back again. Okay, so we have talked about hypothesis function. Now let's talk about cost function, j of theta. So what is cost function? So now we have choose theta 0 equals to 2.5 randomly. But who can guarantee to you this theta is the best? This parameter is the best. So for checking the accuracy of our hypothesis or a model or the parameters of our model, we have a cost function, also called the loss function. Okay, so we have a cost function and also a loss function. So what we do, we theta 0 and theta 1. So what we do is again we check the accuracy with our cost function. So there are two algorithms for that. The first algorithm is mean square error. Mean square error, and then we have a root mean square error. For now, we'll focus on mean square error. Okay, so the equation of mean square error looks something like this. And you might be very kind of thing, something like that. Okay, so don't worry, I will make you understand in just a second. So what we have to check, this thetas. Is this thetas good or not? We have choose the good theta or not? So what we do is with this equation, here m is the size of the training examples. We can take out the m equal m by length of y, or we can say the y dot size. Okay, so you can take out, it's a number for training examples. And what is this doing? So let's understand this equation a little bit more intuitive way. So let's say we have a simple data. You can see here I have generated it from Plotly, and you can see here this is our simple data point, and we have fitted a straight line here. And we have fitted a straight line, you can see here, and we fitted a straight line we're using that hypothesis, and you can see that these are the actual data points, and this is the predicted, this is the model has predicted, and this is again the actual, this is the model has predicted, actual model. So what this cost function does, it takes out the difference between the actual value and the predicted value. So what does this does? So what it does, this equation, let me show you. So what it does, this theta transpose x, it can be written as hfxi. So it can be written as, so it is a predicted value. This is the predicted value, and this is the actual values. Okay, so what we are doing, we are taking out the difference between the predicted and the actual value for each and every examples, and then we are summing it all up and squaring them up. You can see here, and then we are summing them up, and we are this is for summing them up, and then we are squaring them up, and 1 plus m is for a good computation for gradient descent. Okay, so don't worry about this. This is I think so for gradient descent. Okay, so what we're going to do, we are here, what we are doing, we are subtracting the predicted and the actual value, and then we are summing it up all up. So what we are going to do, we are taking out the difference between this, is predicted minus the actual value, predicted minus the actual value, plus, and then we are getting our cost function, which we will store in our J of data. Okay, again the same thing is written here. Okay, now I hope that you got better understanding of cost function also. So there is a direct method for taking out the theta, so we don't have to worry more about, but it is general, not preferred. But I think it is a direct for best theta parameter. It's for a linear regression. So we have a normal equation. Okay, so we have a normal equation. Do research on internet why it is a direct method, because I haven't researched till now, but know what is a normal equation is. Okay, so the equation is x transpose times x minus 1 superscript minus 1 x transpose y. Okay, so this is the equation, and now we'll implement and get our best theta parameter. Okay, so what I will do, I will write all the code, and then I will come back. Okay, so I have written on my code, and what I have written a function. So this function generates the crappy data, or linear cooking data with a Gaussian noise. So this is for Gaussian noise. So it generates the data, and give x and y. And what it does, this is our normal equation. This equation is our normal, oops, I think this is Java, so that's why I'm writing. So this is the normal equation, formula. Okay, so this is the normal equation formula, and this one, what we are doing is that we are instantiating x0 to all training example equals to 1. This is what this np.c does. Okay, and then what we are doing, and then this is the predict method, means again the hypothesis. This is the hypothesis, which is giant vector theta and times the x theta, means the feature vector, which is x. Okay, so it is taking the dot product, and then what we are going to do, we are x and y, which generates the data and plot the data. Okay, so it plots the data. So I will comment in below, and let me show you. So this is the data that we have generated. Now what we will do, we will take out the best parameter using the normal equation formula. You can see here it is the np.len. It is the linear algebra library which will help us to take out to achieve this normal equation. And then we are using this b dot transpose. We are transposing the things. The dot product of x and dot x. Again, we are taking the transpose times the y. Dot product of y. Okay. And then we will call our get base param from this function. So if I plot theta and then run this, so you can see here the base x theta 0. This is for theta 0 because we have only two features, so x and y. So it is a theta 0 and this is the theta 1. Okay, understood what I'm trying to say here? Okay, so now we will plot. So now we'll predict some results. So now we'll predict some results. X to predict. So I made some kind of, now it will predict. Okay, and then what it is doing, we have made our predict and we have our optimal theta, and we provide theta, and you can see here we provide theta. We have got the theta. We provide theta to predict, and we got our prediction into predict variable. Now what we'll do, we will plot the prediction, and you can see here a line, our hypothesis has been plotted. Okay, so now I think that you got better understanding of normal equation. However, search on internet why this is popular. Okay, so this is the equation of our normal equation. Now after some time we'll see this, how do we write a cost function, just in a second. Okay, just the notebook will be given to you, just code me along. Okay, so batch gradient descent, what does that mean? Batch gradient descent means that, let's say you have your theta, and what it does, it gives you the optimal theta parameter. So it will help you to find the best theta parameter. What it does, we simply initialize theta 0 equals to 0, theta 1 equals to 0. It is called a random initialization. We'll talk more about later on. Okay, so in detail when we go to advanced concept, so it is we randomly initialize all the parameters, and then we simply change the parameters using the algorithm, using the gradient descent algorithm, and then to reduce our cost function. It means if our cost function is high, then the error is high. If the error is high, then our theta is not good. And if our cost function is less, or a loss function, then we have a good theta. Okay, so it is directly proportional. Cost function is directly proportional to directly proportional to error. Okay, so what it does, it reduces our cost function. It means that it gives us the good theta parameters. So let's try to understand with the help of an example. So let's take an example that here is our theta. Okay, so here is our theta, and what it does is change and this is our cost function, j of theta. Okay, so this is the ball shaped curve is our cost function, and here is our theta, means we have a very bad cost function. Okay, very bad theta. Okay, so what it does, it reduces it takes baby steps. It takes baby steps. It reach out here, and then it reach out here, then it reach out here, then it reach out here, until and unless it reach out to the global minimum, as you can see in this GIF also. Okay, so and the steps it takes is called a learning rate. If the learning rate, this is the steps taken by the gradient descent, is called a learning rate, and it determines how fast the gradient descent is and how slow the gradient descent is. We'll talk more about just in a second about learning rate. Okay, so it starts from if any kind of random initialization, and it keeps changing the theta parameter until and unless we have a j of theta, means cost function is approximately equals to 0. Okay, let's take one more example to understand things better. So I plotted one more with the help of Python, and I'm not showing the code. The reason is simple, that if you visit the code, you will be moving from this video, so just be there. So what happens, what gradient descent does, so this is the counter plot, and what gradient descent does, it starts with, you can see here theta 0, it starts with a theta 0, theta 0 and theta 1 0 0. So you can see this blue line, theta 0 and theta 0 blue, so it starts from here, and when it takes one step, so the theta changes to 1.4, then it goes the green line here, so it goes here, then theta 0 1.8, then it's gone here, and then this pink line, and then it go further, then this line you can see, and then it's go further, and then until and unless it's reach out to the good or global minimum, and then we got our favorite theta. Okay, so I hope that you got better intuition about gradient descent also, and I think that you are enjoying this session and I'm not boring you so much. Okay, so how gradient descent does this? Again, we have a mathematical equation. So to implement gradient descent, you need to compute the gradient of the cost function with respect to some parameter theta z. So what this is, so to implementation of a gradient descent, or mathematical intuition behind a gradient descent is, what you have to do, you need to compute the gradient of the cost function j of theta with respect to model parameter theta z, and theta z represents theta 0, theta 1, all around theta n. So again, let's understand. In other words, you need to compute the partial derivative of our cost function, that is, how much the cost function will change if you change the theta little bit. Means, if you change theta 0 equals 0 to theta 0 equals to 0.4, how much the cost function will change if you change this theta. If the cost function reduces, we move further changing the thetas. Okay, so this is what the gradient descent does. It's how it's partial derivative states is that how much the cost function will change if the theta changes little bit. It is just like the slope, like how much the xy will change, the x will change, something like that. Okay, so in partial derivative we are talking about how much the cost function will change if our theta will change a little bit. Okay, so again the same thing is happening. Again we have a same cost function, but we have written 2 because of computational complexity, so that's why we have written for easy computational. Okay, so what we are going to do, we are taking the partial derivative of our cost function j of theta, and for taking the partial derivative, you just have to follow this equation. Okay, so in this what we are doing, you can see here j is written. So what this equation does, so let's do step by step. So what it does, first it's focus on theta 0. It takes out how much the theta 0 will change, how much the cost function will change if you change theta 0. Until and unless we found a theta 0. And then we go to the theta 1, and then we go to theta 2, specifically for each parameters. But there is a vectorized form also. And vectorized form also a very good kind of technique. So again the vectorized form is that this is the partial derivative of our cost function. So this is a partial derivative. So what we are doing, we are wrapping up into again this theta z, or we can say the partial derivative of our theta 0, partial derivative of the theta 1, all the way down partial derivative of our theta n into a joint vector, this one. Okay, j of theta, partial derivative into joint partial derivative of j into a vector. Okay, and then it has again the same cost function, vectorized cost function we can say. Okay, and the same thing is here, but we have some kind of vectorized cost function. Okay, and then what we are going to then Okay, so we have computed our how much the cost function will change if our theta changes. We have computed the gradient of our cost function. Now how do we update our parameters? Means we have initialized theta 0 equals to 0 and theta 1 equals to 0. So how do we change, or how do we take the, how do we move to the minimum, how do we move to the global minimum? For that, we have to update our parameter. So if our parameter here, the updated parameter will be here, the updated until unless we reach out to global minimum. Okay. So for taking out gradient step, so for taking out the gradient descent step, so there is equation which is the same, but this is the same as the equation of how this is the gradient. This is the gradient that we have seen above. Means here I can show you. Means here what we have done, this one, and the partial derivative for the cost function j of theta, and then what we are going to do, we are updating our theta parameter, let's say theta 0, we are updating on theta 0 minus the alpha. We'll talk about just in a second the partial derivative for a cost function which is j of theta. Okay, pretty much clear. And if you are asking to step to reach out to global minimum, so that's why we are updating our previous theta parameter with the new one. Okay, so I hope that you got better understanding of our favorite gradient descent. Okay, so you might be thinking, hey, how do I choose alpha? For choosing alpha, you have to tune the alpha, which is a hyperparameter. So you have to choose the alpha, you have to tune the alpha, and you have to try the different alpha rate, and then which works the best, you can choose that. Okay, so if you choose very small learning rate, it will be never convert, it will be very slow. Or if you choose the large learning rate, it will converge, it will diverge, and then it will never come back to global minimum. So you can see here, you start from here, it goes here, then it goes here, then it goes here, like that, diverging. So it never reach out to global minimum. Okay, so my way to think of 0.1, 0.001, 0.00001, just something like that. Okay, just in large data set it works fine, this is a little bit small, and this is very small. Okay, so let's implement a linear regression from scratch. It's already 40 minutes, so I will just come back after writing the code. Okay, so I had this is the very simple very kind of just I'm going to make you understand just in a second. So what we are going to do, we are going to take x, y, the learning rate alpha, and how much iterations we have to do. Okay, and you can take out the m by the length of y, something like that. Okay, and then what we are going to do, we are going to initialize our theta with zeros, and then we will store the cost at different kind of position. So you can remove this, or you can store this for whatever you want. So here, this is the hypothesis, and this is our cost function j of theta. Again, I've written the same formula. This is the gradient descent, and then at last we are updating our parameter theta. You can and we're returning theta, and you can append the cost at different rates, and it will return the cost list. Okay, so this was it for a linear regression from scratch, and this is very easy. And then we are looping over each and every 4 iterations. Okay, for updating, for reaching out a global minimum. So in this way we implement a linear regression from scratch, and I hope that you got better intuition about what I've said till now. And let's implement very fast in linear regression with sklearn. Okay, so what you have to do, we have a simple we are importing the linear regression from sklearn library with the sklearn, and then we are making the object, and then we are making the object, and then we are fitting this does all the gradient descent, cost function, all those things. Not a cost function, it does all those things, means gradient descent. And then this intercept will give you the bias term, and this coefficient will give you the feature weights. And then we are predicting, and then you can score the matrix. We will talk about an end-to-end machine learning project, which will be based on linear regression just after some videos, or maybe in another lecture. Okay, this will be the end-to-end machine learning project. Okay, Okay, so we have talked a lot about and we have coded the things, and I hope that you got better intuition about the things. And please hit the subscribe button. It takes a lot of time to prepare these kind of equations, writing this kind of equation, preparing this notebook for you all. And please do subscribe this YouTube channel and press the notification bell. And in this video I'll be bringing a maybe the project, I'm not promising, maybe the project and maybe the optimization algorithm, another notebook. Okay, so that's it for this video. I'll be catching you on the next video. Till then, bye bye.